Hello, welcome to Lecture 11 of Electrical Circuits 1. Last time in Lecture 10 we introduced Thevenin's theorem and we did a quick example of that. This time I want to give you some more background about that theorem, kind of a non-rigorous derivation of the theorem itself, and provide another example or so. After we've done that, I want to move on to Norton's theorem, state that, and do some examples of that one. Now, Thevenin's theorem and Norton's theorem lead us to a couple of very useful results. One of which is source transformations, which I'm going to talk about just briefly today. The other of which is maximum power transfer. We'll be interested in how we can design our circuit such that we get the maximum amount of power delivered to our load. So I'll introduce this briefly at the end of this lecture, and then we'll get more in depth into maximum power transfer in Lecture 12. Related educational modules are 1.7.4 and 1.7.5. Just to briefly refresh our memory about the goal of Thevenin's theorem. What we want to do is take some complicated circuit, circuit A here, which is actually a black box for us, and we want to replace it with a simpler circuit without affecting the voltage current characteristics at the terminals of this circuit. So any load that we connect to this simpler circuit cannot tell the difference between the simpler circuit and the original complicated circuit. That can simplify our design of this load considerably. Now, I didn't get into why this is possible last time, but ultimately it is due to superposition and linearity. Last time in Lecture 10, I stated rather baldly that any linear circuit can be replaced with a voltage source in series with a resistance without affecting its terminals' voltage current characteristics. So with proper choice of the ideal voltage source voltage and the series resistance's resistance value, you can replace any linear circuit with that series combination. So if I have some complicated circuit A here with a voltage current characteristic at its terminals, I can always replace that with a voltage source with voltage VOC in series with a resistance which we called RTH. The terminal characteristics of this, if VOC and RTH are chosen correctly, are indistinguishable from the terminal characteristics here. Now hopefully when you saw this, your initial response was, why? Okay? Now I want to give you a feeling as to why this is possible. I don't want to do a complete rigorous derivation, but I think you deserve some explanation of why this is true. Now keep in mind that all that circuit B knows about what's going on in circuit A are the voltage and the current at this interface indicated by nodes A and B. Likewise, all that circuit A knows about circuit B is the voltage and current at this interface. So what we're going to do is simplify our life. We're going to take this load circuit and replace it with a current source. So I'm going to get rid of the load circuit. Now I'm going to replace that load circuit with some current source which has current I, so that it's giving me the current that circuit A wants. If circuit A gets the current that it wants, it's going to provide the right voltage. So doing this has not changed the voltage current characteristics at nodes A, B. Okay, we haven't changed anything as far as circuit A is concerned. Now I mentioned earlier that we'll rely on superposition. What we're going to do is show that circuit A can be represented by its equivalent Thevenin circuit by a superposition argument. The first thing we're going to do is kill all the independent sources in circuit A. That means that circuit A is just going to be seen as an equivalent resistance at the terminals AB. Okay? So at these terminals here, if there are no sources active here, this can only look like a resistance. This is going to be the equivalent resistance of circuit A with all the sources killed. So now we have just this resistor with this current source. So our voltage current characteristics here, V1, remember that the total voltage here in superposition is the sum of the individual voltages from the various sources. We've killed these sources. This voltage is now the terminal voltage, which is only due to the sources in circuit B. So V1 is simply RTH times I via Ohm's law. So in step 1, we looked at the voltage current characteristics resulting from the sources in circuit B. Now we want to look at the voltage current characteristics resulting from the sources in circuit A. Then we can superimpose those. So now what we're going to do is replace our sources in circuit A, and we'll kill the current source that was our only source last time. Okay? So now we can get the voltage seen at terminals A, B, which are due to this source in circuit A without the current source in circuit B. So our circuit now looks like this. It has its sources back. It's our original circuit A, but when we kill this current source, it becomes an open circuit. So now there is no current into these terminals, right? It's an open circuit. You can't flow any current through an open circuit. So this voltage here is now due to whatever voltages are applied by circuit A to an open circuit. So V2 is generally referred to as the open circuit voltage, or VOC. So V2 is just VOC. Now to get the total voltage current characteristic due to all the sources in the circuits, A and B, we need to superimpose V1 and V2. So the total voltage is V1, which was RTH times I, plus V2, which was VOC. That's our old expression for the Thevenin voltage. This can always be expressed as a circuit where this voltage is now VOC plus RTH times the current I. That's why any linear circuit can be represented as an open circuit voltage plus a Thevenin resistance in series without affecting their terminal voltage current characteristics. In lecture 10, I listed the steps which are typically done to create a Thevenin equivalent circuit. I want to do that again, only maybe slightly more briefly. The first step is always to identify the circuit for which you want the Thevenin equivalent. Okay, you have to decide what your load is. You have to remove your load from that circuit. The remaining part of the circuit is what you're going to analyze. The terminals that the load was connected to are the terminals that you need to leave open to determine VOC, and the terminals that you need to look into to determine RTH. Now within your remaining circuit here, you need to kill all the sources, look into the terminals that the load was connected to, and determine the equivalent resistance, which is going to be your Thevenin resistance, RTH. After you've got that, you reactivate the sources. Removal of this load will have already left those terminals open, so you reactivate the sources and you determine VOC. Okay, you can determine VOC using any circuit analysis technique you want. So far we've talked about KVL, KCL, Ohm's law, circuit reduction, nodal analysis, and mesh analysis. Any or all of those analysis techniques are appropriate for determining this. Finally, after you've got your Thevenin equivalent circuit, what you typically do is put your load back onto that circuit and use the overall circuit, which is sometimes called the loaded Thevenin equivalent circuit, to do whatever analysis you need to do relative to your load. Now there is one caveat associated with this. This process is only, strictly speaking, true if there are only independent sources in your circuit. Okay, you need to worry a little bit more if you have dependent sources. That information is in the modules and in other sources. We won't really worry too much about that in this class. An example of this. We want to replace everything except this load resistor, which is R, with its Thevenin equivalent. So the problem statement is telling us what our load is. So we want to remove this and take the rest of this circuit as our Thevenin equivalent. Okay, these are the terminals that we're going to be looking into when we're creating a Thevenin equivalent of the rest of this circuit. For the actual work, I'll go on to subsequent slides. Okay, the first thing I'm going to typically do is determine the Thevenin resistance. So I've removed my load from the previous circuit. Okay, I had a current source here. Killing that current source leaves an open circuit here. I had a voltage source here. Killing this voltage source results in a short circuit. Now I want to look into these terminals and determine an equivalent resistance, RTH. This is not connected, so these two here are a parallel combination of resistors. So that becomes a single resistance. Its combination is the product of the two resistances divided by the sum of the two resistances. So it's 6 times 3 over 6 plus 3, which is 18 over 9, or 2 ohms. That's then in series with this 2 ohm resistor. So this is RTH. This is 2 ohms. These are now in series. The Thevenin resistance is the sum of the two, 2 ohms plus 2 ohms, which is 4 ohms. On the next slide, we'll talk about VOC. Now I want to determine the open circuit voltage at the terminals to which the load was connected. So my resistor load is still missing. I've taken that away and thrown it away until I get the Thevenin equivalent circuit of the rest of the circuit. These terminals are open. I've put my sources back in. Now I need to analyze this circuit to determine VOC. Either nodal or mesh analysis should be good choices for this. I think I'll use nodal analysis. I have one independent node for nodal analysis. I need a reference node, which is V sub r is equal to 0. I'm going to choose this as my independent voltage, V sub a. If this is V sub a, this node is constrained by this 6-volt source, so this is V sub a minus 6 volts. Now I can do KCL around this supernode. I have 2 amps going into the supernode. Typically, I'll use currents entering the node as being negative, plus the current through the 6 ohm resistor, which is VA minus 6 minus 0 over 6 ohms, plus VA minus 0 over 3 ohms, plus this current here. If this is an open circuit, however, this current has to be 0. So I add 0 to this and set the whole thing equal to 0. I'm going to move this 2 amps to the right-hand side and multiply through by 6, which gives me VA minus 6 plus 2VA is equal to 12. So 3VA is equal to 18, and VA is equal to 6 volts. Okay. That's given me this node voltage. What I need is VOC. However, since the current here is 0, the voltage drop across this 2 ohm resistor is 0 volts, and VA is equal to VOC. So the open circuit voltage is just VA, which is 6 volts. I'll go to the next slide, draw my final circuit, reapply the load, take a look at the closure of the problem. Now I'm going to draw the overall Thevenin equivalent circuit. I have a voltage source. It is in series with a resistor. My voltage source has to have the value VOC. That is 6 volts from my previous slide. My Thevenin resistance from 2 slides ago was 4 ohms. This is my overall Thevenin circuit. Now if I reapply my load to get the loaded circuit, it's this same circuit, plus minus 6 volts with a 4 ohm resistor. And to that, I can reconnect my load resistance R. Now this circuit can generally be more easily analyzed to determine the circuit's response to some value of resistance. It can be easier to design this resistance from this circuit than from my previous circuit. Now let's look at Norton's theorem. Norton's theorem is kind of a dual to Thevenin's theorem. It looks very similar with some modifications. Norton's theorem says that any linear circuit, okay, we're still talking about the same kind of circuits that Thevenin's theorem dealt with, can be modeled as a current source. So now we've got a current source in our Norton circuit rather than a voltage source in our Thevenin circuit, which is in parallel with a resistor. So I have a parallel combination of a current source and a resistor rather than a series combination of a voltage source and a resistor. So if I have some linear circuit A with some voltage current characteristics at its terminal, what I can do is put a current source in parallel with a resistance that will give me the same voltage current characteristics as long as I choose RTH and ISC correctly. Okay, now let me go through my little derivation of Norton's theorem, kind of comparable to the approach that I took with Thevenin's theorem, but we'll see that some of the parameters take different roles with Norton's theorem. So we still have our linear circuit A that we want to now create a Norton's equivalent circuit of, and we have this circuit B. We're still going to remove circuit B, okay? But we need to keep the same voltage current characteristics at this terminal. With Thevenin's theorem, we applied a current here and relied on this circuit as giving us the same voltage, so we got the same IV characteristics here. Now with Norton's theorem, we're going to put an applied voltage here, which will give us this current I. Okay, this is consistent with what I said earlier about treating these two terminal devices as systems. I can apply a voltage as the input, in which case my current is the output, which is kind of what I'm doing with Norton's theorem, or I can apply an input current, and then my voltage will be the output, which is what we did with Thevenin's theorem. The two approaches are virtually identical. They just represent a different viewpoint towards how we're dealing with inputs and outputs. So notice that I still haven't changed these voltage current characteristics at the terminals A, B. This is still appropriate just the way Thevenin's theorem was appropriate. It's just a different way of looking at it. Okay, with Norton's theorem, we're going to still apply roughly the same steps we did with Thevenin's theorem. We're still relying on superposition. So what we're going to do is kill all the independent sources in circuit A. So in our previous circuit, the only source that's left is the voltage source that we're using to represent circuit B. Okay? So now circuit A just becomes an equivalent resistance, which is the resistance we see looking into these terminals. Okay? This is still the Thevenin resistance. This step is the same regardless of whether you're doing Norton's theorem or Thevenin's theorem. If we do that, this current I1 is now just the voltage difference over RTH according to Ohm's law. Now we're going to go ahead and find the current due to the sources within circuit A. Okay, now if we're going to use superposition, the next thing we want to do is get rid of the source that we did in the last slide and replace the sources that we had gotten rid of for the last slide. So we're going to replace all the sources in circuit A and kill the voltage source representing circuit B. So this voltage source, when you kill it, is going to become a short circuit. Okay, so I've shorted this voltage source. I've got these sources back. I'm going to get the current seen at these terminals. So my voltage difference here is 0. My current is going to be what I call I sub SC. I've changed my direction so that positive is out for no particular reason, really. As long as I'm consistent, I'm okay. So the current that I wanted, I2, is the negative of ISC. So I2 is minus ISC. I'm going to go ahead, short these terminals when I'm finding ISC, analyze this circuit with this condition shorted. That'll give me a number for this current. Now I'm going to superimpose the two components that contribute to the total current at the terminals of my circuit. So I is now I1 plus I2. I1 was V over RTH. I2 was the negative of the short circuit current I sub SC. This corresponds to a conceptual physical circuit. The current here is the negative of this source current plus this voltage over this resistance, which is the current through this Thevenin equivalent resistance. So we see that this representation is equivalent from a voltage current characteristic at the terminals to our original circuit. So our original assertion that we can replace any linear circuit with a current source in parallel with the resistance seems appropriate. Okay, typical steps for creating the Norton equivalent circuit. First, regardless of whether you're creating a Thevenin equivalent or a Norton equivalent, you have to decide what your load is, remove the load, and retain the rest of the circuit. That's the circuit for which you're determining the Norton equivalent circuit. Typically, next, I will evaluate the Thevenin resistance. This step is also the same regardless of whether you're doing a Norton or a Thevenin equivalent. Okay, it's the same thing we did before. The only thing that's different now is that when we reactivate our sources in our circuit, rather than retaining the output terminals as being an open circuit, we're going to short those terminals. The resulting circuit that comes from that process will be analyzed to determine the short circuit current. Okay? Once we've got ISC and RTH, we can use that to generate our Norton equivalent circuit. We can now replace our load, which we removed up here at the same terminals that we have got before, and analyze that load to determine whatever it is that we need to determine. Again, if you have dependent sources in your circuit, you have to do something a little bit different. We won't really worry about that in this course. Okay, as an example of applying Norton's theorem, let's do the same example that we did in this lecture for Thevenin's theorem. We've got this circuit. We want to replace everything except the load resistor, R, with a simpler circuit. Last time we replaced it with a Thevenin equivalent circuit. This time we're going to replace it with a Norton equivalent circuit. So we're going to take a look at this circuit. We're going to determine the Thevenin resistance. We're going to then determine the short circuit current. So corresponding to the approach that I took last time, the next slide I'll talk about the Thevenin resistance. This is the very same circuit that we used the last time we did this example to determine the equivalent resistance. The approach towards determining the Thevenin resistance is the same regardless of whether you're doing a Thevenin equivalent circuit or a Norton equivalent circuit. We already did this. We determined that RTH was 4 ohms. There's really no reason to redo that. Now we need to determine the short circuit current I sub SC for this circuit. These are the terminals to which my load was connected. I need to short across those terminals, therefore the voltage difference across these terminals is now 0. Now I can choose any analysis approach I want to. If I choose, for example, mesh analysis, this will create a constrained loop. This will have a mesh loop in its interior, and this side here will have a mesh loop in its interior. Mesh analysis should result in 2 equations and 2 unknowns. If I choose nodal analysis, let's see, this would probably be my choice for a reference node. If I do that, this is not an independent node. These 2 nodes are not independent. They're constrained by the voltage source, so I really only have 1 independent node if I use nodal analysis. So I'd only have 1 equation and 1 unknown. I'll go ahead and use nodal analysis for this problem. If I choose this as my independent node with voltage V sub A, the voltage here is V sub A minus 6 volts. Now if I do KCL at this supernode, I have a 2 amp current entering the node. I generally take currents into the node as negative. So minus 2 amps plus the current through the 6 ohm resistor is going to be the voltage difference, VA minus 6 minus 0, over the resistance 6 ohms plus the current through the 3 ohm resistor, which is just VA minus 0 over 3, plus the current through this 2 ohm resistor, which is VA minus 0 over 2 ohms. That all sums to 0. I'll take this 2 amps over to the other side, multiply through by 6. That gets me VA minus 6 plus 2 VA plus 3 VA is equal to 12. So 6 VA is equal to 18, or VA is equal to 3 volts. That doesn't tell me directly what my short circuit current is, but it gives me the information I need to find it. So the short circuit current, I sub SC, is just VA minus 0 over 2 ohms, which is 3 volts over 2 ohms, or 1.5 amps. So my Norton equivalent circuit consists of a current source in parallel with a resistance with these terminals. This current source is I sub SC, which I found to be 1.5 amps. The resistance is just our old friend, the Thevenin resistance, which we determined was 4 ohms. This is my Norton circuit. Now my loaded circuit, I take this Norton equivalent, 1.5 amps, in parallel with its 4 ohm resistor, and I reattach the load that I removed to these terminals. So resistance R. We can now analyze this simpler circuit to determine what we need to determine about the load resistor R. Now I want to talk a little bit about what are called source transformations. Our Thevenin and Norton equivalent circuits are essentially describing the same circuit from the standpoint that they describe the same voltage current characteristics of a given circuit. So if I have some Thevenin equivalent circuit here and some Norton equivalent circuit here, if I connect something up to these terminals here, and I connect the same thing to these terminals here, what I'm connecting to the terminals can't tell the difference. It can't tell which of these is inside this black box. So the mathematics that describes these, we said that the voltage for a Thevenin circuit is RTH times I plus the open circuit voltage. The current for a Norton circuit is V over RTH minus the short circuit current. These are not necessarily describing different things. They can be combined and equated. That leads to what we call our source transformations. So the Thevenin and the Norton characterizations of the voltage current relationship are not necessarily independent. They're both describing the same thing. So from the Thevenin equivalent circuit equation, we can solve for the current. So if we divide that equation through by RTH, we get I is equal to V over RTH minus VOC over RTH. We can equate this I to the current that shows up in the Norton equivalent circuit equation. So the Norton equivalent circuit tells me that I is equal to V over RTH minus ISC. This Thevenin equation tells me that I is equal to V over RTH minus VOC over RTH. Those currents have to be equal to one another. This term, V over RTH, shows up on both sides of this equation. I can cancel that out. So I get negative ISC is equal to negative VOC over RTH. So combining my two equations gives me ISC is the same as VOC over RTH. If I solve for the short circuit current, if I solve for the open circuit voltage, I get VOC is RTH times ISC. The thing to note here is that the open circuit voltage that shows up in the Thevenin circuit is related to the short circuit current that shows up in the Norton circuit. If you found one, you don't need to rederive the other one. You can always get the other one directly from the first. So as a generalization of the equivalence of the Norton and the Thevenin circuits is that if I have a circuit which has some voltage source which is in series with a resistance, I can take that combination and replace it with a current source which is in parallel with the same resistance. So if I have this guy showing up in my circuit, I can exchange this part of the circuit with this circuit. I have this same resistance, but I've now put it in parallel with a current source. The value of the current source, according to our source transformation equation on the previous slide, has to be this voltage divided by this resistance. The converse is also true. If I have a current source in parallel with a resistance in my circuit, I can always replace that with a voltage source in series with the same resistance. That voltage source, according to our previous transformation equation, is this current times the resistance. Let's use our source transformation techniques now to analyze a simple circuit. We want to find the voltage difference across these terminals, V, but we want to do it using source transformations. I have a voltage source in series with a resistance. I have another voltage source in series with a resistance. Those two are in parallel with one another. Right off the bat, I can't do anything directly with those. I don't know much about voltage sources in parallel. However, I do know that current sources in parallel add directly. Let me replace these voltage sources with current sources in parallel with resistances. So this circuit here will become a current source in parallel with the same resistance. I still have my 2 ohm resistor here, just moves in parallel with the current source. The value of this current source is the voltage over the resistance. So I is 6 volts over 2 ohms, which is 3 amps. These terminals here connect to this circuit here. This series combination of a voltage source and a resistor can be replaced with a parallel combination of a current source and a resistor. These two terminals here are then these terminals. The voltage is higher here than here. This current source is therefore going to be positive downwards. This voltage source is going to be trying to push current this direction. This current is this 4 volts over this 4 ohms, which is 1 amp. This resistance value does not change. That gives me these voltage difference here is the same as this voltage difference. Now I can add these current sources directly and reduce this circuit. Okay, this circuit is not directly easily reducible. This one is. So 3 amps minus 1 amp combines to a 2 amp source going in this direction, and I have 2 ohms in parallel with 4 ohms. And this is my voltage. This looks like a 2 amp source with a single resistance. 2 ohms in parallel with 4 ohms is 2 times 4 over 2 plus 4, which is 8 over 6 ohms. So now my voltage, V, is 2 times 8 over 6, or 8 over 3 volts. We have one last topic that Thevenin's theorem can help us deal with. That's the topic of maximum power transfer. It turns out that we can use Thevenin's theorem to show how we can provide the maximum amount of power to some load. If I have some load resistance here, quite often I want to get as much power to that load as I possibly can. The way I can design this R sub L is to create a Thevenin equivalent circuit for whatever is driving the load. Then this Thevenin equivalent circuit allows me to choose R sub L very easily. So my design problem is to choose the load resistance R sub L so that this circuit delivers the maximum amount of power possible to the load. For example, in a stereo system, you want to give your speakers as much power as you possibly can. You don't want to dissipate your power in the form of heat in your amplifier. So you're going to choose your speaker resistance or impedance such that your amplifier can give those speakers the maximum power that they can receive. It turns out that Thevenin's theorem will tell us that in order to transfer the maximum amount of power to this load, just choose your load resistance to be the Thevenin resistance. Then you're done. Our previous example from both Thevenin's and Norton's theorems was this circuit with some load resistance. Now we kind of get to see how Thevenin's circuit is going to allow us to design some load. Say we want to choose R such that this circuit delivers the most power possible to the resistance. Earlier we found that RTH was 4 ohms. So this entire circuit had a Thevenin resistance of 4 ohms. Therefore, if I want to deliver the maximum power possible to this resistor, I choose R equals 4 ohms for maximum power transfer. It's as easy as that. Okay, this concludes lecture 11. Next time, we'll do a little bit more on Thevenin and Norton's theorems, a couple more examples. We'll also derive the fact that you can deliver maximum power to a load by choosing the load resistance to be the Thevenin resistance. That deserves some attention. I don't want to do it at the end of a lecture, so I'm going to do it at the beginning of a lecture.